Hello, this is question 10 from the step 3 paper in 2022, the second of the mechanics questions, so another one of my favourites. We've got two light elastic springs, each have natural length A. One end of each spring is attached to a particle P of weight W. The other ends of the springs are attached to the endpoints B and C of a fixed horizontal bar BC of length 2A. Moduli of elasticity of the springs PB and PC are those, S1W and S2W, okay? These values are such that the particle P hangs in equilibrium with angle BPC equal to 90 degrees. Right, let's get a picture up then. So we've got a horizontal bar, which is BC, which has got length 2A. We got this particle hanging down, which is making a right angled triangle. That is at P, which has got weight W. We've got the, what did we say? We've got S1W for that spring. We got S2W for that spring. So I'll call that one F2 as a force. I'll call that F1 as a force. Original length A. So I'll say that's got extended length L1, extended length L2. So I think that's everything in the picture. Part 1, let angle PBC equal theta. Okay, so that angle there. Show that S1 is equal to that and find S2. Oh, well, S2 is going to be dead easy once we've got S1 because we're just swapping from theta to 90 minus theta. So we'll change the sines to cosines and cosines to sines. So that's going to be really easy when we get to that. But we've got to do this first bit. It helps that F2 is perpendicular to F1, so we can resolve along the line BP. So let's get my theta down there. If we're putting another horizontal, that's going to be theta there. So resolving along BP is going to give that F1 is equal to W sine theta. Then we've got the spring. So from the fact that we've got this spring with a certain extension, so the force that we're going to get in the spring is going to be equal to the extension, which is L1 minus A, multiplied by the modulus of elasticity and then divided by the original length. So that's given that. So we're pretty much there already. I just need something for L1. So L1 is 2A cos theta. So right, let's put all of this in. So we've got that W sine theta is equal to 2A cos theta minus A times S1W over A. Lots of things are cancelling here. Get rid of that, get rid of that, get rid of that and that and that. So I get S1 is sine theta over 2 cos theta minus 1. Right, that was pretty easy. And then we've got, so therefore, by symmetry, we've got that S2 is the same as S1, but with 90 degrees minus theta. Therefore, S2 is going to be cos theta over 2 sine theta minus 1. Right, okay, so that's the first part done. There's only two parts to this question. So part 2, take the zero level of gravitational potential energy to be the horizontal bar BC and let the total potential energy of the system be minus PAW. Show that P satisfies that and hence that P equals 0.7 correct to one significant figure. Okay, so we've got the GPE of P, and that is going to be, let's just go back to looking at the picture again. So that's going to be, what have I got? I've got a W and an L1 sine theta. So it's going to be minus as well. So minus W L1 sine theta. Okay, and L1, what did I have for L1 again? That was 2A cos theta, wasn't it? So that's going to be minus 2AW sine theta cos theta. So that's that. Then I've got the EPE of spring 1. So that is going to be my modulus of elasticity divided by the original length times half the extension squared. So L1 minus A squared. So that is then going to be S1 times W over 2A. Yeah, so L1, that was, yeah, 2A cos theta. Yeah, that's what we just had a moment ago. So 2A cos theta minus A all squared. Okay. And well, what S1 was, or what it is this. So that is going to be equal to W sine theta over, well, that A is going to cancel. I can bring an A outside, so let's put an A there, a 2 there. And then, oh, one of those cos thetas is going to cancel as well. 2 cos theta minus 1 is going to cancel. So I'm going to multiply that by a 2 cos theta minus 1. So that's given me the EPE1. So EPE2, well, that's going to be easier to do. It's going to look pretty much the same, except I'm going to have a cos theta, and I'm going to have a 2 sine theta minus 1. Okay, so the total potential energy is all of this stuff. I've got minus 2AW sine theta cos theta plus, yeah, I've got some, there's not an enormous amount to factorise there. Let's just write it all out for now so I can see it all in one place. AW sine theta over 2 cos theta minus 1, and then AW cos theta over 2 sine theta minus 1. Okay, so I've got a minus 2 AW sine theta cos theta. Then I'm going to have an AW sine theta cos theta and another AW sine theta cos theta. So they're all going to cancel out. So let's cancel these things in red. So that is going to cancel with that and that, leaving me with just this thing. Okay, so it's not a lot left. So I've got AW over 2 multiplied by, what have I got? I've got a minus sine theta and a minus cos theta. Okay, and we're saying that is equal to minus PAW. So if that's minus PAW, then so P is going to be equal to a half times sine theta plus cos theta. Right, well, that dropped out okay. And I need to show then that P is sitting between these values. So a root 2 over 2, and that's its maximum value. So that would be when theta is 45 degrees. Yeah, that would give me 2 lots of root 2 over 2, and then I'm halving that. Okay, and then when this has got something to do with, and we've got a root 3 here. So it's got something to do with what these angles are actually doing. So let's think about the, yeah, let's think about these angles then. So let's go back to the picture. So what can I have here? If I add, what are the limits on these things? What's the I suppose the shortest length I could get for BP is A, in which case I'd have a 2A and an A. So 2A cos theta would be equal to A, and that's if I add an infinite modulus of elasticity. So that would be saying that theta would be 60 degrees there. So theta's got to be less than 60 degrees. So theta is less than 60 degrees. Oh, I suppose it's got the other side. If there's then got to be greater than 30 degrees, isn't it? Because we've got the same thing on the other side. Because if 0 extension on one spring, actually that's going to be what we've got here as well, isn't it? Yeah, you're going to see we're going to get that infinite S1. So yeah, i.e. S1 or S2 equals infinity. then we'd have theta is 60 degrees. Okay, so yeah, therefore theta's got to be between 30 degrees and 60 degrees, and we're saying then that it's got a maximum when it's in the middle at 45. So we've probably got a way, if I rewrite this as a double angle at 45, then so how would that work? What would that look like? Maybe do a little aside on this in red. So if I was doing cos of theta minus 45 degrees, what do I want to do? Plus 45 degrees. I think minus is going to be better, isn't it? Because I'm going to want to have a plus inside the double angle. So that would be equal to a root 2 over 2 cos theta plus root 2 over 2 sine theta. So root 2 over 2 cos theta plus sine theta. So this thing then is going to be 1 over root 2, or root 2 over 2, root 2 over 2 cos theta minus 45 degrees. Okay, so yeah, so that helps. That certainly helps. That shows I'm going to get that maximum. Therefore, P max equals root 2 over 2. That's good. And we know that if, well, it's got to be greater than this. So if theta equals, well, let's go, which way should we go? Well, we're going to want to use this thing. So it doesn't matter whether I use 30 degrees or 60 degrees. So let's go 30 degrees. Then P will be equal to a half of a half plus root 3 over 2, which is equal to a quarter of 1 plus root 3. But this is unattainable because S, well, theta has to be between 30 degrees and 60 degrees. It can't actually be equal to 30 degrees or 60 degrees. So therefore, we've got that P has to be, which way round did they've written it? They've written it that way round. It has to be less than or equal to a half of root 2 from this bit, and it has to be greater than a quarter of 1 plus root 3 from this bit. Okay, hence that P is 0.7 correct to one significant figure. Right, that shouldn't be too bad. I mean, let's see if I can squeeze it on this bit of the screen here. I haven't got much space left, but let's give it a go. So I need to show, so if P is 0.7 to one significant figure, so we need P to be between 0.65 and 0.75, and then all is good with the world. So the maximum value, so this means for the root 2 bit then, we need to show that root 2 over 2 is then less than 0.75. So root 2 is less than 1.5. So that's what we need to show. So that's going to be pretty easy. I'm going to squeeze this in a bit because I haven't got much screen space. So root 2 is equal to root 200 divided by 10, because that's just multiplying top and bottom by 10 on that. And root 200 divided by 10 is less than root 225 divided by 10. So there we go. So, 225 being 15 squared. So it is less than 15 over 10. So that's done that bit. And then we also need, so this means we're going the other way on the other one. So we need a quarter of 1 plus root 3 has got to be greater than 0.65, i.e. we need, so 4 lots of that is going to be 2.6, take off 1, 1.6. So we need that root 3 is greater than 1.6. Root 3 is root 300 over 10. and that is greater than, well, let's square the 16 and get 256 over 10, so it's greater than 1.6, or greater than 16 over 10. So write that out again, greater than 16 over 10. Right, so it's quite easy to show something like that. Yeah, just working out some rough numbers that fit with those limits. So that was a nice little bit to tag on the end. Right, that was, again, quite a nice question. I mean, I know I like mechanics questions, but they always seem to be that little bit easier in the step papers than some of the other questions. So yeah, that one went through without too much trouble.